طيب بسم الله الرحمن الرحيم. So last time we finished medium access control, and we talked about different techniques in the MAC layer to control the access to a shared medium, including the collision-based techniques and the collision-free techniques. This part is not actually covered in the book, but I think it's a very important topic, since maybe 70% of the research in related to wireless and networking in general, it kind of touches on radio resource management. In this part, we'll talk about the different concepts related to radio resource management, why this topic is important. We'll touch a little bit on some optimization, although not very comprehensive and not very deep. But we'll give you some idea about the different types of optimization and how can we maximize certain metrics in a wireless network. So radio resource management is the set of components in a wireless communication system that involves strategies and algorithms for provisioning resources. So the network itself has a set of resources. Here we're talking about a network in general, not just a MAC layer on one local area network, but here we're talking about a big network, a cellular network, for example, and we have different resources. We talked about some examples of these resources, including frequency, time slots, power, things like that. We'll talk about this. Radio resource management here talks about the fact that we need to provision these resources for the different mobile stations. الموبايل stations هنا مقصود بيها ايه؟ اللي هي الموبايل equipment that need to take service from the wireless network. And we need to optimize certain metrics for these mobile stations, whether we need to maximize rate, we need to minimize power, energy consumption, things like that. So, of course, radio resource management works hand in hand with the network protocols. So when we talk about standards, they focus on developing protocols. They usually do not get into defining or specifying certain optimization techniques or certain management algorithms, certain resource management algorithm. Usually they leave it up to the developers. And that's really what differentiates, for example, vendor equipment, Cisco from Huawei and things like that. Both of them, they comply with the standards. So their equipment, it complies with the standards. However, there is some intelligence built into this equipment, and that's mainly related to the radio resource management techniques that they have developed in their equipment that differentiates this vendor equipment from the other. Okay? So the radio resource management, they talk about provisioning resources. Examples for these resources including transmit power. Of course, we know the power. Power is energy in unit time, right? So in unit time, how can I control the transmit power? By controlling this transmit power, first of all, you can control the range that this wireless signal can go to. Like, for example, the near-far effect that we have talked about in CDMA. Of course, in CDMA, someone might say, okay, so I will set the transmission power to the maximum so I don't have any near-far effect. But this will not solve the problem. This is one. And two, it actually drains the energy and drains the battery of the mobile station, and that's not something that we want to do. So controlling this transmit power is really key to get the wireless signal enough range for it to perform well. And in some cases, like if we use like antenna diversity, مثلا, or if we use frequency diversity. Frequency here talks about the fact that you send 2 copies of the wireless signal at the same time, صح? And if you do that from one particular device, an example of this we'll talk about in a minute, that the base station wants to send 2 copies of the signal to two mobile stations at the same time. If it uses FDMA, it can do that, right? But that requires the fact that you have to split the power on the two frequency ranges. Okay, so how can you split this power amongst the different frequencies or different antenna? By controlling also the transmit power on different antenna, we can control, we can do beamforming, we can optimize the wireless transmission in a certain direction or something like that. So all of these are examples for how you can provision or split or control the transmit power to enhance the performance of the wireless communication. Of course, channel allocation. We talked about examples of this. So we can allocate time slots. So how can we allocate these time slots to the different users? Of course, if we use TDMA, then we don't have to do anything. It's just fixed. But all the cellular systems, they cannot afford to use TDMA blindly, so because this is not efficient. So in every time slot, you have to perform certain radio resource management to give this time slot to a user that has the best channel. If you give this time slot to a user with the best channel, then this user will have maximum rate. And if this user has maximum rate, he's satisfied. Okay? But there are some issues with this that we'll talk about. Of course, we can split data rates. For example, if we have, if you remember in antenna diversity, we talked about the fact that we can split the traffic into two different data streams. So what data stream you send here and what data stream you send here, what is the traffic rate here, what is the traffic rate here? So that's also something that you can control, right? Depending on so many factors, depending on the channel gain, and we'll talk about channel state information and so on. Handover criteria, of course, you will get to experience this in assignment 3. So handover criteria, this is very important. So by handover, we mean that a mobile station is moving, and now it's moving from the range of one base station to another, right? So when it moves, then it needs to leave that current base station. But which base station should it connect to? All right, so it has access to many other base stations. So what is the base station that has the best criteria from the perspective of this mobile station? Okay, so this handover criteria could be that I connect to the base station that I have the best wireless channel with, or the best signal, or maybe the base station that gives me the maximum rate. Maybe one station can allocate to me a few time slots. This base station allocates to me one time slot only, right? So regardless of the channel condition, I will connect to the one that gives me the maximum number of time slots. So because this will allow me to get maximum rate and so on. So this handover criteria is also something that we provision or we can control, right? Depending on whether this base station is busy, this base station is not busy, things like that. This mobile station is far, this mobile station is close to one, and so on. So the easiest way is to just connect the mobile station to the base station that's closest in terms of distance, but usually this is not the most efficient. So that's also something that we can control. By modulation scheme here also we mean that we talked about QAM, so we can use 4 QAM, or we can use 64 QAM, or 128 QAM, right? So 128 QAM seems very attractive because then you can squeeze and you can have spectral efficiency, very high spectral efficiency, because you can squeeze many symbols, right, in the same time slot, right? But this will lead to the fact that the symbols are very, very close to each other, and that usually leads to high bit error rate, right? So which QAM level or which constellation level you can use, okay? This is also something that you can control. And that's usually based, all of these, you will find that there is a very important factor of what is the state of the channel at this point of time, okay? So if you have a stateful algorithm, different from the fact that you don't have a state. So if you have a state, which means that you have a channel state information. We'll talk about this. This is very important. If you have channel state information, then you can optimize things more efficiently. If you don't have channel state information, then you will have to shoot in the dark. You will have to take certain decision and then see how it looks like and so on. And that's why now most of the research in wireless communication has switched to machine learning and reinforcement learning, because using these tools, you can now, it talks about model free and so on. So now you can, if you have channel state information, then you can use some stateful machine learning tool like reinforcement learning. If you don't have channel state information, then you can use bandit learning, you can use anything like this. So all these tools have evolved in wireless communication because of their ability to deal with radio resource management. Also, error coding schemes. We have different types of, if you have studied this before, error coding schemes here talk about some redundant bits that gets added to the packet, and these redundant bits are usually used to sometimes to detect if there is an error in the packet, or in some cases you can correct the error in the packet. By increasing these redundant bits, you can detect more errors, okay, or different combinations of the errors, and you can correct these errors if they happen. So by increasing these redundant bits, you can address a larger spectrum of errors, but at the same time also you increase the overhead, right? Because each packet now will have another, packet next to it, like of redundant error coding bits that are used to control the errors, right? So by increasing these redundant bits, you can detect more errors, but you can increase the overhead. So what is the trade-off in between? Okay. So all radio resource management, they talk about addressing trade-offs. They talk about the fact that these resources are a commodity. These are scarce resources in the network, and we need to control them very, very efficiently, because we don't have enough capacity for everyone. And there is always a race between upgrading the network, and users are increasing and diversifying the services that they need to use. So the network is getting upgraded, but at the same time, users are using different services. They need to watch now YouTube more frequent. They need to have like high definition video, TV on demand, and so on and so forth. So these services are growing, and also we keep upgrading the network, and there is a race. So that keeps radio resource management a very, very hot topic and hot area. It's always a hot area because even we are growing the network, but at the same time we are also growing the services that get supported on this network. Okay. So the idea here is to utilize the limited resources, the limited radio resources. It's always limited, even if we're talking about 5G, and even when we talk about 6G, it's always limited. Okay, so we need to allocate it carefully. And radio network infrastructure. We'll get to experience that in assignment 3. So we have infrastructure. How many base stations do we have? How many mobile service controller and base station controller and so on? We'll talk about the cellular architecture. Maybe next lecture we'll talk about how we allocate resources in each of these architecture components. So we can allocate the resources in spectrum. We can allocate resources by spectrum. Here, of course, we mean frequency, or time slots, or codes, or power, and these are some examples of these resources. Type a simple wireless or a simple motivating example here talks about how a base station can allocate power, or the transmit power, in two different streams or two different wireless signals, right? By using antenna diversity, or by splitting the power across two antennas that communicates to one separate mobile station. So this is a very famous example. So this is optimization in the downlink. So a base station wants to send wireless signal to two mobile stations. So it can actually perform this either using a frequency diversity or antenna diversity. So it can use two different frequencies and split the power across the two different frequencies, or it can use two different antennas to communicate, and in that case it also splits the power between these two antennas, two or more طبعا. Okay. So the idea here is how can we have this GI is the channel gain for user I. So The idea here is that how to split the transmit power. When the transmit power gets multiplied by this gain, right, it leads to a specific signal-to-noise ratio on this particular stream. Signal-to-noise ratio, which means the relation or the ratio between the signal power and the noise power, right? So this gain is composed of three main components. There is the antenna gain, which is the transmit antenna gain. So this is like the amplification gain of the antenna itself, right? So this is the analog gain that the antenna itself gives to the signal. And there is, of course, the path loss gain or attenuation. In that case, this is the path loss where the signal attenuates normally while it goes through the air, right? So this alpha here represents the attenuation exponent in this particular environment. So the vacuum, I think, the alpha here is 2 for the vacuum. So even for the vacuum, still you get some attenuation. But usually in normal environments, you have air, you have dust, you have things like that. So the attenuation is slightly above 2, which means that the signal attenuates a little bit faster than the vacuum. The vacuum is the ideal environment. In any case, this is another type of gain that affects the wireless channel. So you have the antenna gain, and you have the attenuation, and you have the fading gain. This fading gain is a complex number or a complex channel gain that affects the signal. It can actually change or deform the signal, as we have talked about. So fading here talks about multipass fading, right? And of course, there is the receiver antenna gain. So all of these components, they constitute the total gain for the wireless signal. So again, the gain from the antenna, the attenuation, the fading, and then the antenna gain at the receiver. Okay. So this is the gain that the signal goes through. Okay. What you can control here is the transmit power from the base station. Okay, so this is the optimization variable, or this is the one that you can control from the base station. Okay, so the big question is, how can we allocate this PI, right? Would you multiply it by the gain and divide it by the noise power? Okay, we can estimate the rate for any mobile station. How many of you are familiar with this Shannon equation? Okay, anyone else is familiar? So basically, this is something حتى you don't even need to memorize. If there is an exam or something, I will give that equation to you, so you don't have to memorize. Basically, Shannon says that you can estimate the achievable rate, in any wireless channel by knowing these components. This is the bandwidth of the channel that you transmit through. So basically, the rate is linearly proportional to the bandwidth, which makes sense. By having more bandwidth, you can increase the rate. So this is this is basics, and then it's proportional to the logarithm of the signal-to-noise ratio. This is what we call a signal-to-noise ratio. This signal-to-noise ratio is the relation between the transmit power, or the wireless channel power, and the noise power. This is the noise floor, or the noise power, right? So by increasing the signal-to-noise ratio, or in other words, by having a transmit power which is much higher compared to the noise power, obviously, as you can see, you can increase the rate, but logarithmically, not linearly. Okay, so this is what Shannon said. And this is the equation, by the way. This is very basic. This is the equation that we use in wireless communication heavily, okay, to estimate the rate for any wireless channel. What we do is that we estimate all these by channel gains to try to estimate the rate, and based on that we can control certain parameters to try to maximize this rate. So our objective is how to optimize this rate. And of course, Here, this is RI. What we need to maximize is the summation of all RIs in the mobile stations. Okay. So again, this is the gain of the channel. This is the transmit power. This is the optimization variable that we talk about. This is the noise floor or the noise power per hertz. When we multiply it by the bandwidth, we get the noise power for the entire bandwidth duration.
The only thing we can control here is
the transmit power, PI. That's it. Okay. Of course, here you can do tons of research here. So you can control, for example, the antenna gain. You can work on optimizing the antenna gain. You can work on optimizing even the fading gain somehow. You can control many things, but what we need to do here, the simplest example here is just to control the PI. Okay. So if base station can transmit with a maximum power, how to allocate this available power? Of course, any hardware, any physical hardware has a limitation in terms of the maximum power it can use, right? So it's not unlimited, obviously. And by power here, we mean the definition of power is energy per unit time. Huh? So here we're trying to send two signals or more, but at the same time. So we have to split the power. So how to allocate this available maximum power, okay, amongst the two mobile stations, or potentially more than two, okay, if we have more than two. In other words, what is P1 and what is P2? Okay, of course, someone might say, why not make them equal? So P1 equals P2 equals P over 2, خلاص, equals this P over 2. Okay, this is good, this is fair, and okay. But of course, this will not necessarily have the maximum aggregate rate, as you can imagine, because the gains are different. The gains of the channel, at least something that you cannot really control 100%, is the fading gain, مثلا, or the attenuation. That's not something that you can control, right? This is physical. This is something due to the physical environment that you use for transmission. So this is not something that you can control, right? So using equal power is not usually the most efficient. An example of this is, of course, for the case of CDMA, the near-far effect. We know that we cannot use the same transmit power because the receiver power will be different, in which case you may have near-far effect for CDMA, for example. So you have P1 and P2 such that in P1 plus P2 is the maximum transmit power. Okay. Of course, that could be extended to sigma of Pi equals to P if you have multiple mobile stations. So let's just equally divide them. And by the way, in many cases, based on our hatta research and based on our experience, in many cases, sometimes equal power is not bad. In certain cases, it's not really bad, and we'll see that. But there are certain contexts where equal power is not good. Okay. So if we use the same power, and if we assume that P is 5 watts, so we can 2.5 each. We can use 2.5 each. If we have gain 1 equals 1.5 and gain 2 equals 0.5, if we do like a small substitution here, we get R1 equals 224 and R2 equals 117, in which case this is the total rate that we get. Is this maximum or not? At this point, we don't know, right? How do you prove that something is maximum? You prove that there is nothing else more than this. صح? Usually that takes some proof, and we usually, مثلا, the most famous one is that we have to define a function, and then by maximizing this, we take the derivative and make it equal to 0, صح? Make it equal to 0, and then we can estimate the P1 and P2. In that case, if P1 and P2 leads to the fact that the derivative is 0, then it's maximum. صح? We have this.
So the Shannon equation does not give the maximum rate.
لا Shannon equation estimates the rate ملوش دعوة هو بالماكسمايزيشن. We need to maximize that. But using Shannon rate tells you that you can estimate the achievable rate. هو ما بيقولكش حتى ان this is what you will get exactly in practice. الراجل ما قالش كده. What he claims is that this is the achievable rate if you have a signal to noise ratio characterized by these parameters. This is the achievable rate, okay? So the alternative is how to maximize R1 plus R2, okay? This is the objective. By maximizing R1 and R2, or R1 plus R2, sorry, because maximizing R1 and or R2 is a totally different objective. But maximizing the aggregate or the summation of R1 plus R2, ماشي? This is good from the user's perspective, right? So the users are getting aggregate rates, and that means that the vendor or the service provider is happy because the aggregate rate is good, right? But we'll see that there is some issue with this. But this is subject to the fact that we have P1 plus P2 less than P, صح? This is what we call a constraint. So in optimization, this is called the constraint. So this is called constraint optimization, right? Maximizing a function, it's easy. We took that in calculus. We know how to do this. We take the derivative equal to 0, and then we can... we can say that we take the partial derivative of R1 plus R2 with respect to P1 and with respect to P2, and then each one will equal to 0. So we know how to do this. The problem with this types of problems is that constraint optimization, we cannot just straightforward use the same derivative. We cannot do that because this will allow us to achieve the absolute maximum of the function, but not necessarily the one that fulfills the constraint. In order to visually appreciate this, if you assume مثلا ان احنا عندنا one parameter يعني حتى P1 or P2. So the function looks like this, such that there is an absolute maximum point. And at the maximum point here, the slope, we know that from calculus, huh? The slope is 0, right? So we get the absolute maximum. But if you draw the P1 plus P2 less than P, this will actually get you some kind of straight line like this. This is a linear يعني constraint, right? And anything below that, right? So definitely the absolute maximum here does not fulfill the constraint, right? Because here we say this is maximum, but P1 plus P2 is less than P, right? So the absolute maximum of this problem does not really fulfill the condition. But if you want to really achieve the one that achieves that constraint, then it's probably here, right? صح? So this one here achieves that condition, and at the same time, it's the maximum. It leads to the maximum function or the maximum value for that function. Can you visualize? Can you? Okay, so of course this one is higher, slightly higher than this, so that leads to probably higher value for the function. So this is probably the one that fulfills the condition. How can we achieve this? We cannot do straightforward derivative and get this يعني in using straightforward ways يعني, right? So we have to get into some constraint optimization. And also another challenge here is that the derivative, by the way, gives you يعني the points where the slope of the function is 0, right? صح? What if there are multiple points where the slope of the function is 0? For example, something like this. So the function is something like this. Okay? If the function looks like this, then you have multiple points where the slope is 0. Right? So there are we call them a local maxima or local minima. Okay? So if you want to maximize the function, then it should be one of these points, in which case the derivative will not help you that much, right? But if you use the derivative, then you have to take these points and also see which one is the global maximum. So we call these types of function a non-convex functions. For non-convex functions, they have many local minima and local maxima. So if you don't use the proper technique, like an example, the one that we will talk about in a minute, then you will get trapped into local minima or local maxima. Okay, so you will get some value for power, or you get some value for the decision parameter, but it might not be the global maximum. Right. So usually the steps or the systematic steps for solving these types of optimization is that first you need to prove that the objective itself is convex. If you prove that the objective is convex, then what you need to do is to achieve one point only to maximize or to minimize, and that will be enough. Because for convex optimization, there's only 1 point maximum or 1 point minimum. That's it. Okay? If the function is not convex, then it's a problem. Usually we use some other tricks and techniques to transform the objective into something that's convex, and then map the solution from it. Something complicated. We don't have to get into it. ماشي? But usually for gradient descent, but هو احنا will use gradient descent.
يعني machine learning we are trying to minimize the cost of the
yes. لا بالضبط صحيح. ما هو for machine learning حتى we use forward propagation and backward propagation to use gradient descent to minimize the objective. ماشي? And the objective in our case is to minimize the loss.
Yes.
صح? The loss is the difference between the expected label and what you achieve at the output layer. صح? This is what we do. So it's similar. So we use gradient descent. However, in machine learning, we use what we call a stochastic gradient descent, right? Because gradient descent requires that you have to achieve the derivative for every point in the data set, and usually this is not achievable. But we use stochastic data set, stochastic gradient descent. Anyway, we don't have to know this part at all. But this is just to motivate you that learning this stuff allows you, by the way, to do very strong research. And most of the publications they have strength when they talk about these issues, rather than just taking a simple tool, applying data set, get analyze the output, and that's it. So what is the contribution here? I can ask anyone, even in high school, to do that. So what is the intelligence? What is the modeling part? The key here is how to really convert your real life problem into an optimization framework like this. This is what we call modeling. So this modeling part is usually the most important part. Understanding the background behind optimization helps you to try to design the proper techniques to solve the optimization efficiently. But remember, there are very powerful tools to help you to do this. There are solvers in Python, there are solvers in MATLAB, very strong solvers, even for non-convex optimization. There are some tools to help you to do non-convex optimization, okay? But understanding these concepts at least helps you to try to model correctly and apply the model into the solver correctly, and then when you get the result, you interpret it correctly, okay? You are not deceived by the output. So far so good. Okay. So this is اتفضل.
How much the level of abstraction will be moved? Like,
This is the engineering aspect of it. This is the engineering aspect of it. We'll talk about some tricks and some techniques for modeling. Because here, there are some issues, by the way. In this modeling, you will discover after a few slides that there is a big issue with the way that we model this problem now. This is a primitive way of modeling this problem. We'll talk about many issues related to that. Okay? So we know that for any function, if the function is convex, then this function has one and single global minimum or global maximum. And this is perfect. This is good for us. This is good to know because if we take the derivative, we get 1 point, there is no ambiguity. صح? خلاص, there is no ambiguity. This one where the slope is 0 leads to the maximum or the minimum. And it's only 1 point. This is good. ماشي? So we know for a function like this, a logarithmic function like this, we know how to take the derivative. Of course, the derivative, when we say the derivative equals to 0, we can get the value of x, and the value of x happens to be, this is len يعني. ماشي? We know that the derivative of len x is 1 over x. And this leads to the fact that x is 1 over e. خلاص. And there is no ambiguity. X equal 1 over e, it's only 1 point, and this is the minimum. Okay? The problem for us is that we have a constraint. So for example, for this minimum, we have a constraint that looks like this, and we have to consider anything above that. Right? So in that case, we have to achieve this point, not this. So what is the tools that allows you to get this? This is what we need to discuss. So for optimization, it's different. So for example, this is a problem with constraint. So this is a quadratic function. We know quadratic function is always convex. It's good. It's always convex. Convex in x and convex in y. So there is no issue. However, how can we deal with this constraint بقى؟ فجه بقى الحاج Lagrange is one of the scientists who said that I can convert the constraint optimization into a non-constraint optimization by adding this constraint to be part of the objective. Okay, so I can get this constraint and say and make it equal or يعني I have to take everything on one side and make the other side 0, right? And then take this. So when you minimize here, this has to be greater than. When you maximize, this has to be less than. Okay? So by doing this, we can say, okay, so it's x plus y minus 1 greater than 0. And then take that part, put it in the objective, and multiply it by ده بقى اللي بيسموه Lagrangian multiplier. Okay? This is an auxiliary variable or an added variable, okay, that hopefully at optimization, it doesn't matter because we will try to get a solution where x plus y equals to 1. If we have x plus y equals to 1, then we don't care about the value of lambda because خلاص, it's multiplied by 0, so we don't care. ماشي كده? So once we do this, what we could do now is that instead of having an objective, which is a function of 2 variables, now we have an objective which is a function of 3 variables, including lambda, right? So we know how to deal with this. So we take the derivative of that non-constraint objective with respect to x, with respect to y, and with respect to lambda. What you will see here is that when you take the derivative with respect to lambda, you always end up with the constraint. And we will try to get the solution that achieves x plus 1 equal x plus y equals to 1 exactly. صح? Because this is when this derivative equals to 0. And that's what we want to do. ماشي? So by doing this, we converted the constraint problem into non-constraint problem, and then we can solve 3 equations and 3 unknowns. we know how to do this. صح? We are masters in doing this. So it turns out x equals 1 over 3, y equals 2 over 3, and lambda equals 4 over 3. However, we don't care about the value of lambda anyway, because if x and y equals to 1, then we don't care. ماشي? So this is the point that really achieves the objective with the constraint. واضح كده؟ So this is one of the very famous tools. Of course, there are tons of other tools and other concepts where you can that you can use to solve constraint optimization, and that's what I'm saying. There are many solvers in Python, in MATLAB that you can use for solving these optimization frameworks. But the key is how to model the problem correctly. Like what Abdurrahman said, it's actually this is an engineering aspect بقى. ماشي? And you can model this is the main contribution really. In my opinion, this is one of the main contributions in any research, because you can model the problem in a way that's attackable. So one reviewer gets into the problem, hey, what are you doing here? You are neglecting this, you are neglecting that, this is too abstract, you are not taking into consideration very key aspects, and so on and so forth. So the modeling part is key, because solving the optimization after this is pretty much straightforward. طيب, let's go back to our main problem is that we need to use the same technique to convert the constraint optimization into non-constraint optimization. So we can convert the problem. So we know this is the Ri, صح? This is Ri, and we take the summation of this, and again this is the constraint, and we added a lambda, right? And because this is a maximization problem, lambda here is added by minus. This is the maximization problem, right? So at optimization P1 and P2 equals to P, in which case lambda we don't care. ماشي? So we can take the derivative of L with respect to P1 and P2 and lambda. So this is I'll just do the derivative for Pi, and the rest is easy. So of course خد بالك هنا. This is log 2. This is log 2. We know that the derivative of len x is 1 over x, but this is len is the base for len is e, صح? But you can prove easily that log 2 of x equals to log len x divided by len 2 اللي هو البيز. صح كده؟ ماشي؟ So we have to convert this log 2 to len something in order to use the rule of 1 over x. So we know how to do this. ماشي. طيب, so isn't the derivative of L with respect to Pi is equals to first W, doesn't matter, and then this 1 over, so 1 over 1 plus Pi Gi divided by W n0, right? So this is 1 over x, and then you multiply by the derivative inside the function اللي هو ايه؟ اللي هو Gi divided by W n node. Okay? صح كده؟ I may do mistakes, خد بالك, راجع ورايا. Okay? Of course, here there is len 2, صح? This is len 2. ماشي؟ ففي len 2 هنا يعني. Doesn't matter, it's fixed يعني, it's constant. And this is equal to 0. And of course, the derivative of L with respect to lambda is P1 plus P2 minus P equals to 0. So now we have 3 equations in 3 unknowns. We can achieve P1, P2. So it turns out if you get the summation of these gains, okay, then it leads to what we call the average gains amongst all the channels. ماشي? And we subtract this part for the particular user that we want to allocate the power for. Okay? We call this algorithm, by the way, water filling. Water filling here talks about the fact that if the user has high gain, then we can give him high power so that we can achieve high rates. That's what that means. If the user has low gain, then this user has bad channel. If we give him high transmit power, this means that we are wasting that resource because he has a low channel gain or gain across the channel. So if we give him high transmit power, this means that we will not achieve the rate that we want to maximize. Okay? So this means that we have an average, or we have like a water level كده, and then based on this, we try to give a resource to the user to get him up to that level. We try to allocate the PI that get the user up to that mu level. Okay, so it looks like this. So this is mu, and this is water filling. So this is actually اللي هي G divided by WN node. Okay, if that's greater than mu, this means that I do not, because if I assign a transmit power to that user, I need to use a power which is above P. And that's not possible أصلا. So it's not feasible. يعني this user has really bad channel. I cannot give him any transmit power that will get him any rate. ماشي? So in that case, I assign 0 transmit power. Okay? And then I assign transmit power based on the difference between mu and this gain. واضح كده؟ عشان كده they call it water filling. It's as if you have like different tanks and you have a water level, and then you want to keep each one at this water level. So you have to fill the water up to this level and then you stop. That's why they call it a water filling. واضح كده؟ ماشي كده؟ طيب. So by doing all this optimization بقى, let's see how much we achieve. So this will lead to the fact that P1 equals to 3.167, P2 equals to 1833, and it turns out that this user has really bad channel, so we give him a little bit of transmit power will lead to this. So here, this is the total rate. Remember the rate for the equal allocation was how much? 341. 341, right? So by doing all this optimization, we have gained only 4 kilobits per second, which is nothing, maybe 2%, 3%, something like that. Okay, so that's why I'm saying that in some cases, equal power allocation is not bad, but at least here we understand the concept, because in some other contexts, لا, it makes a big difference. It makes a huge difference. ماشي كده؟ Any questions so far? Are you following type في حي مشكلة؟ Okay. خلينا نستوب. So we have seen that despite all this optimization and good stuff, we have achieved only 4 kilobits per second, which was a bit of a news. So network's throughput is maximized by allocating most of the power to the user with better channel. And this is logical. So if we assign higher transmit power to the user with good channel, you will achieve high data rates. Okay. So user with lowest channel is, on the other side, is suffering, right? So, but is that wrong? Just because of the fact that he has bad gain, does that mean that that this mobile station is bad? No, it just happens that it's really unfortunate that this mobile station is far from the base station at this point of time. So that's not the problem of the mobile station. So on other side, so the service provider should not really care absolutely for maximizing the resource utilization on the cost of the users with bad channel. In other words, there has to be some kind of a fairness. Because if we work on absolute maximization or absolute minimization, we usually forget or avoid the issue of fairness, right? So we end up with users are not taking any resources from the network. And that's not good. They are not, I happen to drive a car and I got far from the base station, so I'm unlucky and I don't get resources. That's not the way it should work. صح? So there has to be some kind of fairness. But how do you achieve this fairness? Fairness is not a binary thing. It's not a binary thing. As we all know, absolute fairness is like we give everyone exactly equal share. And usually, برضو, actually, by doing this, we're not fair. Even by doing this, we're not really fair. Okay? So we'll talk about some examples that the most fair algorithms are actually not that fair as we think. So another class of optimization frameworks is called maximum fairness. So these class of optimization techniques, they don't care about maximizing the rate. They care about maximizing the minimum rate. And what that means is it tries to shorten or lower the gap between the user with the maximum rate and the user with the minimum rate. So they are trying to shrink that. By shrinking this, we try to be fair to the users with the bad channel. Okay? So if we do the same problem by maximizing the minimum rate, and here we're maximizing for any I, right? So here, what we're trying to achieve is that we take the maximum R and the minimum R, and we're trying to shorten the gap between them. Ideally, we need to make them very, very close to each other. Okay? So by doing this, we can, طبعا using the maximum fairness, طبعا for maximum fairness, by the way, we use different solvers. We use different techniques. Lagrangian والكلام ده will not really help. So we use different optimization techniques. Fortunately or unfortunately, we don't have to get to the details of this. But if we use maximum fairness, then PI is equal to 1.25 and P2 is equal to 3.75, in which case, as you can see here, we achieve the rate, which, طبعا here, the rate is equal, which is good. So by doing this, again, being fair doesn't mean that you allocate equal power. You try to allocate in such a way that achieves the lowest gap between the maximum and the minimum. And here, the gap is 0. So they are the same. So this is good. So we achieved fair, not fair allocation, but the fair performance, equal performance. But by doing this, we had to spend more effort for the guy with the low channel in such a way that we have achieved a total rate of 304. So that's a way lower than what we have achieved before. So from 345 in the case of maximizing the rates to 304. So we have lost maybe like more than 25% of the total rate to try to be fair, right? واضح here? So this is maximum fairness. So which one is good? So that's about how you convince the reviewer that actually absolute fairness usually is not really good from the perspective of resource utilization. So this way the users are maybe happy, and the user with bad channel is really very happy, but the service provider is not happy because the total rate is low, which means that the total resource utilization for the network resources is actually low. صح? So the weak user has a better throughput now. However, this comes with the expense of lowering the throughput for the strong user. And in that case, the total throughput is actually lower. So another class of optimization techniques that tries to address some trade-off between the absolute fairness and maximizing the total rate. This is what we call proportional fairness. So we try to achieve proportional fairness. ماشي؟ الحياة فعلا عايزة proportional fairness. يعني we talk about يعني I get to some gender issues. So we have gender equality or gender equity. صح? So we have different characteristics. We have different requirements in life. So the absolute fairness is usually not really good. It's not really fair. We need to give different resources to different entities, okay, in such a way that we try to achieve some trade-off between fairness and also high performance. Okay, and that's what we try to do in communication. We always try to use proportional fairness. Okay. So the basic idea for achieving that trade-off between spectral efficiency and fairness, okay, is for different bandwidths and power and some performance criteria into a corresponding utility. This utility is just a function that tries to integrate into it this proportional fairness. Okay? It tries to integrate into it some aspect from fairness and some aspect from the maximum rate or some spectral efficiency. This utility, you can think of it as measuring the satisfaction of the user by performing or by provisioning certain network resource. How satisfied this user is, okay, is actually what this utility tries to measure. ماشي? So a guy with the bad channel, if you give him something good enough for him to browse the internet and stuff, he might be actually very satisfied. Okay? But at the same time, I try to use the remaining resources to try to maximize the resource utilization of the network, in which case I try to also have users with good channel to really have good rates, in which case I can try to address some trade-off between the two. So these utility functions are used to quantify the benefit of usage of certain resource, or in other words, the satisfaction of the user as a result of provisioning certain resources to that user. ماشي? For each user I, we define a function UI. This utility is called utility optimization. So this is another class of optimization techniques. So xi could be the rate in that case, could be ri, right? But the utility here, it's actually a function of ri, not ri straightforward. It's a function of ri, right? But can we define this function in such a way that achieves this trade-off, or achieves what we call proportional fairness? It turns out that this is possible. Okay? طبعا we've been talking about the rate, but it could apply for delay, for packet loss, for any other metric, right? So instead of maximizing the sum rate, we'll maximize the sum of the utility, or the aggregate utility, subject to the constraints similar to what we have done. A very famous utility that really achieves this, and we'll talk about what is the intuition behind it, is instead of maximizing Ri, we'll maximize log Ri. Okay? So instead of maximizing the summation of Ri straight, we'll maximize log Ri. Why? Because on one hand, this log Ri will achieve the proportional fairness, and I will try to motivate why this is happening. And on the other side, log x usually does not change the convexity of x. So if x is convex, ماشي, then log x is also convex, which is good news because we don't want anything that transforms the problem into an unconvex optimization will deviate from our objective and will try to make it difficult for ourselves. واضح كده؟ So log x, the good news is that it does not affect the convexity of the problem. ماشي? Which means here that we will maximize log 2 of 1 plus SNR log SNR كده يعني log 2 of 1 plus log SNR. ماشي? So this problem is this function is still convex. ماشي? So so if we do this, then by maximizing log 2 of r, the intuition behind it is as follows. So if you assume that Ri is actually a function of any decision variable, let's say مثلا bandwidth. Bandwidth. This is bandwidth, W. And it happens that R is linear, صح? As a function of W, it's linear. So you have something like this, linear. ماشي? So this means that by provisioning more bandwidths, ماشي, Ri will increase with the same proportion. And this increase will keep forever. By assigning more bandwidths, you get more R. Assigning more bandwidths, يعني it's proportional, linear. By doing this log 2 بقى, we are changing this relationship to something like this. صح? This is log. معايا? So how does this achieve that proportional fairness? The intuition behind it is conceptually acceptable. Why? Because when we increase the bandwidth, okay, at the beginning we increase the rate almost linearly, similar to what we want to have, right? But after certain limit, ماشي, the increase in the utility will start to decrease. So the gain that you're getting by assigning more resources is actually decaying, which will force you to try to give others amount of resources to keep them in this region. معايا? So this will allow you to try to allocate the resources in such a way that at least you keep everyone in this region, ماشي, and give each one minimum share of these resources to give him some level of satisfaction. And if you still have some budget, ماشي, you can start to give it to the user with high channel gain. Okay? So this will allow you to gain more utility, but the increase in the gain will decrease the more you give this user more resources. So this will discourage you from giving very high resources to user with good channel and have other users starve because of the fact that you have bad channel. واضح كده؟ واضح الانتويشن behind it? So this is يعني intuitively acceptable, and it turns out it has some mathematical proof, and really it proves to work efficiently in practice. يعني. So that's this type of utility-based optimization is also a way for us to transform the objective of the problem, to move it to another domain. We call this transformation. So sometimes we use this log to make the problem convex. Okay? So we use sometimes this trick to make the problem convex. So sometimes if Ri is not absolutely convex, if you take the logarithm of something like this, you actually convert it in the convex domain. So you transform the problem into something that's convex, and in that case, you can solve it using some very efficient techniques of convex optimization. ماشي? So this is what we call utility-based resource allocation, and that achieves some kind of proportional fairness. So this is similar to this example. This is a very famous example on social media. You see this picture a lot.
Okay.
So it's not really about this. It's not about giving people equal resources. This is what we call equality, right? But what we really need to do is proportional fairness. Proportional fairness is not absolutely fair, but it keeps the satisfaction level of all the users very well, in a very good level, and that's what we need to achieve, right? واضح كده؟ So this is what we call a proportional fairness. واضح؟ في أي سؤال؟
لا.
تمام؟ طيب we have at least يعني some intuition why this log R is actually proportionally fair, and it tries to maintain a balance between the two competing interests, maximizing the network throughput and allowing minimum quality of service to the users. So we will try to keep everyone at least in the minimum in the linear region by assigning minimum amount of share, right? And then we use the remaining budget to give it to the user with high gain to maximize the resource utilization. So we achieve some trade-off between the two. طيب, very importantly بقى, a big assumption, there are many assumptions that we did implicitly when we modeled the problem this way. One of these assumptions is that we have complete knowledge about channel state information, which means that we have perfect knowledge about this GI. We know the fading gain, we know the distance, okay? So we have some estimation at any point of time of the distance and the fading gain. Say the antenna gain is easy. I know the antenna gain because it's local, right? So I can measure the antenna gain easily because this is in the hardware. But the channel gain, how can you measure it? It's a question. Of course, there are some techniques to estimate it, okay? And also, we need to measure the distance in order to estimate the attenuation gain. This is collectively what we call the channel state information. So the optimization problem that we have just gone through assumes that we have perfect knowledge of this. Because GI was completely known. But in practice, this may or may not be possible, okay? Depending on whether the base station actually performs measurement, whether the mobile station supports this kind of measurement, because how can you measure the channel state? You have to send a wireless channel, and then the mobile station will send you some feedback. By doing this, you measure by signal strength, and you can estimate by some channel gain and so on, right? And also estimate the distance. Estimate the distance requires triangulation بقى وأشياء زي كده يعني. It's possible, but it requires some information that it may or may not be available at any point of time, and it may be available partially كمان. ماشي? So it may be available but partially. ماشي? So if we take this problem and assume perfect channel utilization, then this is what we have done so far. We may assume actually statistical channel state information. Statistical, which means that we don't have an instantaneous, but we have some average over time. مثلا. So we have some idea, but we don't have complete idea. So that leads to stochastic optimization. That's a different class of optimization. So by making certain assumptions, you can change the problem significantly. ماشي? طيب, this is from the channel state information point of view. If we assume بقى that instead of working downlink, we work uplink, ماشي? Which means that we have some mobile stations and we have the tower, ماشي? But here بقى the traffic is maybe going this way, and the base station also need to control the data in the uplink, ماشي? Such that also the aggregate rate is maximized or proportionally fair or similar to what we have done, right? But in that case, there are there is some extra piece of information that I may or may not take it into consideration, which is what we call state queue information. So each of these users, they have some traffic which is going from the network layer, مثلا. It's building up in a queue. ماشي? So this queue has limited buffer. So in addition to channel state information, you have also queue state information. ماشي? طيب, how does this make the problem different? It makes it significantly different, because just the fact that I have a good channel, it doesn't mean that I get to transfer packets at this point of time, because there are some other users maybe with worse channel, but their queue is building up very, very fast, and if I don't give them the chance to transmit now, then they will fill up the queue and they will start to drop the packets. Okay? So this example, this assumes مثلا TDMA. If I want to allocate a time slot to a particular user, which user should take this time slot? It's not a power splitting problem here. It's actually assigning time slot to a user. Should I assign the time slot also to the user with the best channel? Maybe yes, maybe no, depending on the channel state and the queue state. So if I take the queue state into consideration as well, then the problem becomes much more complex. ماشي? So queues are filled at different rates, and the resources are allocated such that the queue length are kept bounded. So I don't want the queues to build up very fast to the extent that they start to drop packets. That's also not a good situation. Sometimes there is a correlation between the queue state and channel state, and sometimes there is no correlation. And that also changes the dimension of the problem. Anyway, so there is the interference level. Because if I assume that we have مثلا a cell, so this is a base station and we have some users, and these users are sending data in the uplink, but we have another cell here. ماشي? So this user is in the boundary of two cells. So this user actually suffers from some interference from the other cells. So the level of interference has not been taken into consideration in the previous problem at all. Okay? So this user suffers from some levels of interference. This user maybe does not suffer the same level of interference. So in that case also, that affects the channel state information, and it also affects the solution significantly. Because signal-to-noise ratio here, signal-to-noise ratio takes into consideration not the noise power and the interference power as well. And that takes the problem in a totally different dimension. So all of these are things that we ignored totally in the modeling of that previous problem. ماشي? On top of this all of these factors are time varying. So just the fact that we have channel gain at this point of time and we perform the optimization, right? We come up with P1 or P2, P1 and P2, تمام? Or we come up with solution that optimizes the queue states and خلاص, everything is good. After 1 second, everything will be different. The channel state information will be different. ماشي? The gains will be different. The queue state will be different. صح? Everything changes over time. So our optimization problem, by achieving the optimal values for P1 and P2, after 1 second, P1 or P2 will not be optimal anymore. واضح كده؟ طيب, so how can we resolve this? Should we run the optimization problem every 5 milliseconds, every 1 second, every 2 minutes? Adaptive. يعني you change the frequency of how often you run the optimization problem. Right, that's yeah, ماشي, okay, بس adaptive based on what برضو? This is the question. طبعا what we are طبعا this is بقى why AI has done revolutionary advancement in this field. Because AI بقى and reinforcement learning in particular deals with these time varying issues. Because I can have an agent to learn the variations of the channel, the statistical distribution of how the queue changes, and then learn how these factors change, and then perform actions that will not only optimize بقى the metric at this point of time, it actually optimizes the accumulated benefits over a long period of time. But in order for me to do this, I have to have some idea how these values change, how these states change. So if I have channel state information and queue state information and maybe some other state information, I can define or model the problem as a reinforcement learning. Here is the state variable. I can define a reward function. I can define action. Action اللي هو إيه? How can I allocate power? How I can allocate time slot? Things like that. This is the action. And model the problem as a reinforcement learning problem and come up with a solution that not only will maximize the performance now, but it will maximize the performance even over time, while these values are changing over time. Okay? But the limitation here is that how I can have this agent learn the environment. So I have to build some simulator or some digital twin or something like this that will allow this agent to learn in a synthesized environment. And then hopefully when I take that learned agent and deploy it in practice, hopefully it will perform close to how it was performing in the simulator. Anything that's hard, difficult so far? Did I lose anyone? Still following? Okay. طيب. These metrics بقى احنا again so far احنا we're talking about maximizing the sum rate or maximizing the total throughput. ماشي? The sum rate or the total throughput. This is one example. Another thing is to minimize the delay. And instead of maximizing the throughput, I can minimize the delay. Okay? What is the difference between the two? Fundamentally different. How يعني is different? Because maximizing the throughput, it means that throughput is a bottleneck thing, but the delay, you can take into consideration multiple types of delay. So you have transmission delay, you have handover delay. You have different types of delay. So I want to minimize maybe not only the transmission delay, but I want to minimize the total delay, which includes مثلا transmission delay, propagation delay, handover delay, and different types of delay. ماشي? Throughput is throughput, but delay has different components. I can even minimize the number of drop packet, or what you call a drop rate, or dropping probability. ماشي? Maximizing network lifetime, that's a very interesting one. Usually we use these types of metrics in مثلا sensor networks or ad hoc networks. Okay, maximizing network lifetime. So maximizing network lifetime, we mean that we want to keep this network operational for the longest period of time. You have possibly مثلا a network of drones or wireless sensor networks or ad hoc network. ماشي? So you have nodes like this, and I want to maximize the lifetime of the network itself. Maximizing the lifetime of a network does not necessarily mean maximize the lifetime of a node, because I can lose a node, but the network is still operational. Okay?
So what do you mean by lifetime? You mean like supply power?
أيوة شفت ما أنت قلت. There is no single definition for the lifetime of a network. There is no single definition. Okay? Some people, they say the lifetime of a network is the lifetime until one node at least dies. Or the lifetime of a network is the time until all the nodes die. Or the time until the network becomes two networks. ماشي? And what that means is if you have a network like this, so you have some communication from any node to any node, صح? If these nodes die, then these nodes cannot communicate with these nodes. They disconnect from each other. So the network becomes actually two networks, two isolated networks. So you say that the lifetime stops here because you have some disconnectivity in the middle of the network, or some part of the network is isolated from the remaining part of the network. Okay? So you say that the lifetime stops here. So there are different definitions of that. And this of course, this is very complicated to do, especially in ad hoc. Imagine بقى you do this optimization problem to maximize the lifetime of a network of drones, or a network of wireless sensor network, or ad hoc network. Some autonomous cars are moving and they need to communicate something to each other for مثلا accident avoidance ولا أشياء زي كده. And you need to maximize the lifetime of all of them. And they have some electric cars, مثلا, they have limited power, things like that. And you have to do some provisioning of the resources and use the different transmit power in order to make them operational for the longest time possible, something like that. It becomes really complicated. Usually, طبعا, in certain context and certain problems, you cannot even model as an optimization problem. Or sometimes model it, but you cannot really solve that optimization problem because it's highly non-convex. So usually modeling the problem as an optimization framework is actually a contribution on its own, but solving this optimization problem is not necessarily possible. You can just resort to some heuristic techniques or some AI-based techniques or something like this. Okay? But you try to model the problem as an optimization just to show that solving the optimization straightforward is not even possible in practice. And actually, in many cases, it's not even practical. ماشي? Because it requires gradient descent and some iterative techniques which you don't know how much it takes. And you have to do this very frequent. واضح كده؟ معلش الحاجات دي على فكرة it gets covered in many courses, by the way. So we're just assembling some flowers from each field But we talk about key concepts that I think can open the door for some research ideas for you. Yeah, so this is a very famous problem that for مثلا GSM or second generation wireless, it uses TDMA and TDD. TDD for uplink and downlink, so it actually divides the problem into 128 مثلا time slots in uplink and 128 slots for the downlink. And then the idea is that in uplink and downlink, you can assign these time slots to different users. Depending on what بقى? Depending on so many things. Do I have channel state information? Which user has the best channel state information at this point of time? Should I have absolute fairness, no fairness, proportional fairness, things like that. واضح كده؟ So for TDMA, if I want to allocate the time slot to different users in such a way that it's absolutely fair, right? Which means that one time slot to a user, and then 1, 1, 1, 1, 1, and then I recycle 1, 1, 1. This is called a round robin, which means that we take turns. That's what we do in TDMA. So TDMA is essentially uses what we call in radio resource management. It uses what we call a round robin. For round robin scheduler, it's absolutely fair. Of course, it's fair, 100% fair. Is it efficient? Of course not. It's not efficient. But the good thing about it is that it's very simple. And by the way, something is missing here. No need.
Synchronization.
لا, synchronization has to be there. No need for channel state information. I don't even need to measure channel state information, ولا queue state information. I don't need anything. I'm just assigning one time slot to each user blindly. ماشي? I don't need channel state information, which is good. It's very simple. But is it really efficient? Of course not. So here it achieves maximum fairness or even absolute fairness. ماشي? Anything like that, anything other than this requires channel state information, at least partially, or يعني, part of it. Okay. So if I gather channel state information, so users with the best channel state information, they get assigned the time slot. So if I do this, then I maximize the resource utilization. So that's the other extreme. So we have round robin, absolute fair, and we have the allocating based on the best CSI. Okay, round robin in terms of complexity is O of 1. So I don't need to search anything. If I need to allocate time slot for the best CSI, this is O of n, bravo عليك. So for each time slot, I need to have a vector of all the CSI, okay? I select the maximum one, and this will be the user I assign to take this time slot. So this is O of n, ماشي? Given that I have the channel state information. واضح كده؟ How can I achieve that in this particular example? How can I achieve proportional fairness? This is about what we need to achieve. So we can do the same, but based on Q state. So by using the channel state information, we can select the one with the best channel state information, and then we assign the user to this time slot. And this will be يعني maximum in terms of resource utilization. We can do the same based on the queue. We can select the user with the maximum queue length and give it a time slot. واضح? So this is also O of n, right? But in that case, the objective is slightly different. And instead of maximizing the resource utilization, we are trying to keep the queue size bounded. So this will actually guarantee the queue length is bounded. صح? Because we keep selecting the user with the maximum queue. ماشي؟ طبعا this technique can be hacked very easily. So if someone hacks a certain user and sends any dummy packets, the whole network will be down in that case, because this user will always have the maximum, the longest queue, and in that case, all the time slots will be wasted on that user. So this can be hacked easily. صح كده? So this is a hacking technique for security. تفضل. Yes, exactly. The number of UEs. The number of UEs.
Yeah, for one station.
لا, the number of UEs اللي هي user equipments.
Yes,
Connected to the base station.
Yes, one.
The base station is one, yes. The base station is one, and I have N UEs or user equipments. So the time slot, the base station decides this time slot will be assigned to which user. So for these techniques, I need to scan all the users one by one, and I check one thing only, either the channel state information or the queue state. And based on that, I decide. So this is O of n. واضحة كده؟ واضحة مش واضحة؟ Okay. So there is طبعا على فكرة this is a heuristic technique. يعني احنا when we say that the assumption that we assign a slot to the user with the best channel state information, we did not prove that this is optimal. In order to prove that this is optimal, then we should try to formulate the rate and we see whether this algorithm achieves the maximum or not. We did not do that, صح? But it turns out, yes, if you do this, you actually achieve the maximum. But in order to prove it, you have to go through mathematical derivation. ماشي? Another class of heuristic techniques is to check this ratio for all the users. Okay? And then assign the time slot to the user with this maximum factor or this maximum metric. ماشي؟ طيب what is this metric بقى represent? This is TDMA, right? Okay, so in each in each time slot, each user has instantaneous rate Ri. By instantaneous rate here, I mean if you have a particular channel state information, I can estimate signal to noise ratio, and then I can estimate the achievable rate for this time slot. This is the instantaneous rate. ماشي كده؟ واضح؟ And then here, I have Ri of t plus 1, and so on. So all in each time slot, I have an instantaneous rate for this particular time slot. The capital Ri is actually the average rate across multiple time slots. ماشي? Which means that the accumulated rate that this user achieves over time. Or in other words, the sigma of instantaneous Ri over t, over this time duration. ماشي؟ يعني if he takes the first slot and the third slot and the fifth slot, he has an instantaneous rate in each of these slots. If I get the summation of all these instantaneous rates and then divide it by the total time, then this is the average rate. ماشي؟ So if I divide or I measure the ratio for all the users between the instantaneous rate and the average rate, I can have very interesting techniques by just controlling alpha and beta. ماشي؟ So in fact, with this technique, I can achieve proportional firms. Again, we have to prove it mathematically, but it turns out that this is possible. So R here is the rate achievable for the user for the current time slot, and capital R here is the average rate over time. ماشي؟ طيب alpha and beta here are tuning parameters بقى. If alpha is 0 and beta is 0, and beta is 1, sorry, so this means a 1 over Ri. So in that case, all I need is to control the average rate for the user. I don't care about the instantaneous rate. I care about the rate over time. ماشي؟ The rate over time. So if the user has bad CSI in one slot and good CSI in the next time slot, the average might be the same. صح؟ صح؟ In which case, over time, I can actually probably neglect CSI, which leads to something like round robin, because I don't need even CSI, right? All I need to do is just to control the average rate. So over a very long period of time, if I do round robin, they will be the same. صح? And that's what I need to do here. I need to only give the time slot to the users in such a way that 1 over Ri is maximum. بس. ماشي? So by controlling the alpha to 0 and beta is 1, it's actually a round robin. It's equivalent to round robin. Not exactly, but it's equivalent to round robin. If I take alpha 1 and beta is 0, this is actually maximizing Ri. صح? Which is the maximizing the network throughput. ماشي؟ واضحة دي ما فيهاش حاجة. By having alpha is 1 and beta is 1, this is actually proportionally fair. Why? Why? Because if يعني I need Ri, the component of Ri will help me to try to care about maximizing the aggregate throughput at this time slot. صح? Which contributes to maximizing the network's throughput. But if over time I see that this particular Ri is taking so much resources, the average will go up, which will take this ratio down. صح? So this will discourage me from giving that user extra resources. It's similar to the log. ماشي? So also this ratio is similar to the log. So that's also another trick that you can use to guarantee or to try to enforce the network to be proportionally fair.
And also to resolve the issue of the attack you mentioned.
لا, here we're not taking the queue into consideration at all. We're not considering the
For
queue
the round
خالص.
robin,
For the round robin,
yes. The round robin, it keeps giving the, for example,
لا, هو round robin here gives time slot to each user blindly, regardless of the queue state.
does not check the queue.
لا لا, هنا ما فيش queue state خالص. هنا ما فيش queue state خالص. واضح؟ متابعين يا شباب؟ كله تمام؟ Okay. So just by controlling alpha and beta, I can achieve any class of fairness or maximization I want to have. ماشي كده؟ تمام؟ كفاية ولا كفاية؟
We have today, sir.
يا خلينا 5 minutes كمان عشان بس okay. طيب, so far we talked about this optimization in infrastructure networks. So if I have a centralized architecture where I have base station and multiple mobile stations, so you see how يعني variable or how much variety of problems we have discussed so far. It's plenty. All of this assumes single hub. So either downlink or uplink best. Okay. But if we talk about بقى multi-hub networks, example for multi-hub networks include بقى drone-based networks, ad hoc network, mobile ad hoc networks, sensor networks, all of these types of networks. In that case, the devices, they communicate directly to each other without having any base station or coordinator or anything. زي مثلا Wi-Fi direct, Bluetooth. ماشي? So all of these standards, they assume ad hoc communication. طيب. So why the radio resource management in ad hoc communication or ad hoc networks is dealt with differently? Because for multi-hub communication here, the problem becomes decentralized. ماشي? So in all the problems that we have discussed so far, we assume a centralized controller which is running in the base station and it controls everything. And that's doable. Usually the centralized controller makes things easy. If we assume بقى ad hoc, this means that everything is decentralized. Okay? The other issue is that if we have يعني مثلا, this is a motivational example. If we have a network like this and it's wired network مثلا, okay? And imagine that this link has a rate or maximum rate R. And this link has a maximum rate R. Okay? What is the maximum traffic rate between this source and this destination? ايه؟ يا راجل. R. صح? Okay. So you have one session goes from the source all the way to this. It's one session. ماشي? So here the rate is a bottleneck parameter. If you have multiple hubs, then you have to see the link with the lowest rate, and this will be the maximum rate you can achieve because it's a bottleneck. ماشي? The delay is an accumulative parameter. You have to calculate the delay here, and it will be the summation. ماشي? طب this is in wired. What about wireless بقى? If I have a wireless link, here and a wireless link here, and I can send, assuming here on this link, I can achieve a rate of R. And if I do this, I can achieve a rate of R. Okay? What if I do this? What is the rate?
Either one of them.
Either one of them, which means what is the total rate? أيوة.
Between maximum R.
لا maximum. No.
Between R1 and R2.
No. What is the maximum?
Not the summation.
ايه؟ Average. ما هو الافريج R. R plus R divided by 2 is R. Okay.
Can be 2R. Yeah, 2R. Could be maximum 2R.
In wireless, I'm talking about wireless.
The state of the channel.
In a way, that's true.
What's the answer؟
What's the answer?
يعني لا
It depends on the state of the channel. This is partially true, yeah, but statistically, it's actually somewhere around R divided by 2. Okay? Hmm?
Noise something very
No, it's not about fairness here. It's about the fact that the traffic here has some interference with the traffic here. This did not happen at all in cellular network because all of us, we send to the base station if we use FDMA, TDMA or something, there's no interference. صح? But in ad hoc network, لا, it's different بقى. يعني if this traffic, if we send at the same time from here to here and from here to here, we may have collisions. They may actually collide at this point. ماشي? So this is 2 hubs, right? But the traffic on these 2 lengths, it may actually interfere with each other. So may achieve something like R over 2 plus or minus.
So with more hubs we get less.
Yes. تخيل بقى. شفت بقى? This is bad news. ماشي. And this makes the problem of radio resource management in multi-hub networks really يعني a daunting problem. A real complex problem. So imagine بقى if you have radio resources on each of these lengths and you need to control how you provision the resources on these lengths. The most challenging thing here is that the control of these resources itself is decentralized. So who would control these resources? You don't have base station, you don't have a centralized controller. And this is بقى called بقى ايه? Distributed optimization. So we're touching بس on يعني I did not يعني these are covered in courses, not just one course. بس I'm just giving you some motivation. اتفضلي. هو peer to peer ده from the application point of view. احنا physical layer و data link layer. ماشي. Here احنا we assume that this link is wireless and this link is wireless. Peer to peer ده لما نيجي نقولها امتى في الابلكيشن layer. Application layer yes it's peer to peer طبعا. صح. بس the application layer does not take into consideration ولا بقى contention ولا collision ولا application layer مش علاقة معايا. بس احنا here we're talking about physical layer and data link layer. So if we send from this node to this node, the transmission range goes beyond, and if it goes beyond, it can interfere with this traffic. Okay? واضحة دي؟ Yeah, from the application layer, it's peer to peer صح، بس هو we don't take into consideration in the application layer, we don't take into consideration all this contention و collision والكلام ده ما بناخدوش في الاعتبار. Okay? So in our بقى communication level, we have to worry about these things. And achieving بقى or controlling the radio resource provisioning in these types of problems becomes really يعني hard. So going back to the philosophical question of Abdurrahman about the level of abstraction for modeling the problem, yeah, it's up to you. It's up to you. But you can see the varieties of things that you can work on, and you can make certain assumptions to always يعني have a boundary of how complicated your problem is. One of the traps that many or some people they fall into is that they try to take everything into consideration and come up with the most complicated problem, and then they sit down and try to find a solution, and they wait for sometimes 8 months. Wallah, I had an example of a postdoc, PhD, PhD holder. He stayed like 11 months trying to find a solution for a modeled problem. And I kept pushing him, I kept convincing him that this is perfectly unsolvable. Please try to make assumptions to make things يعني reasonable. ماشي? As long as there is some differentiation from the state of the art, you have an added value. Jump into this. This is the low-hanging fruit that we want to achieve. Our objective is not to find the perfectly unsolvable يعني problem and try to find a solution where the solution does not even exist. ماشي؟ فهو he kept looking for the solution for 11 months, and after 11 months he told me, you know, this is not solvable using the straightforward optimization techniques, so I'm going to learn machine learning in order to solve it. So I told him, very good, thank you very much. But يعني don't try to be perfectionist, because you see the level of sophistication that you can get through. And that's why you need some guidance, because sometimes you don't know how complicated this problem is. So you fall into the trap of يعني this is too complicated and it has no practical solution at least, and yet you try to spend months and months to try to solve it. In these types of problems, you can just try to resort to heuristic techniques, suboptimal techniques, and it's good from a practical point of view. It's good. This is good enough. Okay. تمام. خلاص فاضل one slide. That's a very good point. That's a very good point.
You should be patient.
That's a very good point. We always try to have trade-offs. ماشي؟ أنا عايز أصنع المعجزات. I have a very long objective to achieve. I don't have to achieve it in my degree يعني. ماشي؟ You can achieve it in your life. زي مثلا someone is trying to invent a time machine and he's spending years and years, 30 years. Maybe you can have small projects that would lead to this, but you don't have to solve this problem in your degree يعني. Otherwise you will not graduate. ماشي؟ You always have to address some trade-offs in your life. I'm not sure if this is convincing to you, but it's reality. You have to also live reality. ماشي؟ يعني you have to be يعني reasonable.
Like you look for small wins.
Huh?
You look for small wins, and you grow it all to a big one.
Yeah, exactly. Divide and conquer. ماشي? You try to achieve a very far-fetched objective by dividing it into smaller pieces. So maybe you say, okay, so I want to achieve this after 5 years, 10 years, but I want to divide it into smaller pieces. So I want to solve this problem now. So it's all about trying to come up with some research questions. These research questions collectively will lead to something really revolutionary or something like this. That's fine. That's what they did in حتى ChatGPT and in all disruptive technologies. This is what they did. يعني ChatGPT would have been real if they don't have this work of Google, like attention is all you need. ماشي? And if they don't have all the advancements in NLP before that. So everything tries to accumulate to each other. أيوة بالضبط كده بالضبط. Not reinvent the wheel. ماشي? This is very important. Anyway, so given بقى suitable constraints on interference, because interference بقى is a big issue for multi-hub communication. Multi-hub communication interference is an issue that you cannot really get around. And you can get around in cellular network by assuming that you have a single cell. Single cell خلاص, you don't have interference. الحياة حلوة. That's fine. You can simplify things. Multi-hub لا, it's all about interference. هو all the traffic they interfere with each other. ماشي? So in that case بقى, you need to know بقى if you schedule things using بقى TDMA. But TDMA here is done for the multi-hub network. In other words, which link you should activate at this point of time. So if you activate this link, and sometimes if you activate this link and one link far from it, you have zero interference, in which case you can activate these two links at the same time. ماشي? But don't activate two links close to each other so they have interference. How do you schedule this in a distributed system? It's not easy. So you have to take QoS into consideration, and you have to take back this QoS in an end-to-end fashion. Because in multi-hub communication, you have end-to-end sessions. ماشي? It's not a single hub anymore. You have to have end-to-end sessions, and each session might go through 3 hubs, 4 hubs, 5 hubs. Okay, so we have to assume that's why when we talk about network slicing, in networks, we always assume end-to-end slice. We have to achieve some quality of service across end-to-end. ماشي كده? So this is the last slide. ماشي? So it's hard to collect information about the network at a centralized node. So this is what we're saying. So control is inherently decentralized, and this is a big issue. So which link, which as the node, performs the optimization? ماشي? Let alone that optimization is relevant at this point, and after a few seconds, this optimization will be obsolete, and we have to run it again and again and again. So there is also a trade-off between completely centralized and completely distributed. Distributed here meaning that all these nodes, they have to run some local technique to schedule resources in one node, right? So this is the other extreme. Or you collect all information and run optimization in one node. This is the other extreme, right? Or in many cases we resort to somewhere in between اللي هو بيسموه بقى ايه clustered optimization. So you have a cluster of nodes, and each cluster has some head of cluster, and this head of cluster collects information in this particular cluster and then performs part of the optimization, and these clusters, they communicate together, something like that. ماشي? So these are the two extremes and the spectrum in between. ماشي كده? Any questions? Sorry to take a long time.